now we'll begin with the session given by Professor Stefan Wabnitz from University of Rome. He will be talking about nonlinear optics on fibers. And well, since this session is sponsored by Optica, we must thank them for bringing Stefan here in Valencia. And it's also included on the conference cycle of the Faculty of Physics. So Albert, as in charge of this cycle, will also represent again Stefan. Thank you so much for coming, for everyone in the workshop and everyone outside of the workshop also. And yeah, I give it to Albert.
Okay. We have to thank many people today. First of all, I would like to congratulate, our student chapter of Optica, who organized this nice conference. So as I told them that they are doing so well that maybe they will be required in future times to do it again. But this conference, as Mark said, it's also part of the cycle of conferences. With this one, we will close the scientific conference of the current course. And today we had the opportunity, because of this link between this conference and this cycle, of having one of the most eminent researchers in this nonlinear fiber optics field. So for me, it's really a pleasure to have here Professor Wabnitz, who I didn't know personally. I know many of his papers. And Professor Wabnitz, I think, is remarkable that he's currently in the University of Rome, but he's been professor in other places, right? You were professor at Brescia, right?
Right.
And also at Dijon,
right.
Bourgogne. But what was more remarkable for me was that you also had some career outside the academics, right? Mm-hmm. So you were also in some companies doing technical assessment there, which somehow is telling you that, telling you both, all of you, that it's a very nice combination of, academy and applications in a field in which you could see that it's related to something which is very applied, but you can also do very interesting physics in it. His background is engineering, right?
Right.
So you'll see that you can do many things, no matter if you are a physicist, mathematician, or engineer, so if you are good enough. So I just want to give him the floor to start with this conference that I will hope it will be, and I'm sure it will be very interesting for all of you. Okay, thank you very much. So we can start. Go ahead, please.
So thank you, Mr. Chairman, for a kind introduction, and in particular to the student chapter for organizing the entire event and being in contact for several months for all the details of the organization of this interesting event aimed at young researchers. So I encourage you to. I am a little bit uncertain about, there is probably a different level of expertise among the audience, the young researchers who are here. So I encourage you to even, maybe it's a little bit difficult, time is short, but if you have questions, maybe even better to interrupt, to ask questions right away rather than waiting until the end. So that's always what unfortunately it happens rarely in lectures that the students have the courage to interrupt, but that is the most constructive approach if there is it's not just a unidirectional message, but it is the exchange is bidirectional even during the exposition, and not only waiting for the question and answers part of the talk. So that is the general title, as it was mentioned, is Nonlinear Multimode Fiber Optics. And actually the subtitle of this presentation is from wave thermalization to extreme nonlinear optics. So it's really focused on some physical and aspects and new vision and results that we have obtained in our group in Sapienza University of Rome over the last 5 years. So we got started exactly in 2019, and it's a new lab. And I would like to mention my young co-workers, Ferraro, Mangini, Pararivas, San, and Zitelli. And that's where we are, in a beautiful place. I think you can recognize this building from the Gladiator movie. So that is our faculty is located in it was the monastery of the Church of St. Peter in Chains, which is just next door. So that is the cloister, the courtyard of our engineering university, which is off the main campus of Sapienza. And our nonlinear photonics lab was established 5 years ago, thanks to a grant by the European Research Council, an advanced grant on exactly this topic of complexity and multimode optics as a test bed for studying complexity in physics and in nonlinear waves. So these are pictures of when our femtosecond laser platform and optical table were carried out, were mounted in our lab exactly 5 years ago. Oh, sorry. So here is an outline, and I would like to mention that, in fact, this presentation turns out to be a tutorial talk that I presented at the last Clio Europe in Munich. So it is a tutorial, so it is intended to be presented as an introduction to the field. So I will, my focus will be to really expose you to some ideas and concepts, and maybe inspire new developments, new directions, without going too deep into the details, which any of you who is interested can explore by looking at the papers. So I would like to introduce multimode nonlinear fibers, why we are interested to study them, and what's the difference with respect to single mode fibers. There are two types of telecom or conventional multimode fibers. There are many specialty optical fibers like microstructure fibers, hollow core fibers, and so on, which I will not have time to talk about. What is interesting is that, in fact, these are commercial fibers, step index or graded index fibers that have been developed already before single mode fibers, already in the 70s, when fiber optics, all business of fiber optics for communication started. So I will motivate, and then I will introduce. So that is all the stuff. But then there is a new diagram that we have. I would like to present, which is introducing to really new concepts that we have somehow discovered from the practice of our lab. So it was not something that we had an idea that all these things will happen, but actually we observed them and we understood them on the way, thanks to young people, young researchers, and their imagination. So there are two main regimes: weak nonlinearity, where nonlinearity is relatively weak, is a perturbation with respect to the guiding structure of fibers. And there are a couple of effects that I would like to present. Multimode solitons, which is a generalization of optical solitons in single mode fibers, which just celebrated the 50 years anniversary last year from the prediction by Asagawa. And then another effect, which is relatively new, and which is actually the one that motivated, that gave the birth, for this advanced grant, that is the beam self-cleaning effect in multimode fibers. It's a very surprising effect, and a new thermodynamic theory has been developed, also in collaboration with other people in France and in the United States, and which sort of explains, even though not explains everything, but it gives at least a good prediction that is confirmed by our experiment, even though there are still open questions that I will not have time to discuss today. And then there is a whole another, let's say, playground, which is on another scale of optical powers that we call extreme nonlinear optics in multimode optical fibers. That is when the power grows so high when you approach the damage threshold of the fiber, and some beautiful effects like generation of a rainbow spiral from the fiber, helical plasma filaments. So we observe plasma filaments that typically are observed by powerful laser beams in air. We can observe them in fibers, and also some surprising effects. I mean, fibers, they are known for being transparent, so they have a very, very low loss, and that's why we can use them for the backbone of the internet, let's say highway, of the information highway. But in fact, those very high powers, then there is nonlinear absorption effects, like multi-photon absorption, which is induced by very small defects in the fiber, and that leads to up conversion of light, which leads to luminescence. So we are able actually to see the beam of light by this luminescence that is scattered out of the fiber. So it's a whole new regime that, in fact, nobody studied before, that only occurs at very high power levels. And then I will conclude. So what is the difference for starters between single mode and multi-mode fibers? Well, there is a very simple difference from undergraduate students. Simply the size of the core is bigger, which means that we can understand the behavior of single mode fibers or multi-mode fibers by just ray optics approach. We have many rays that can propagate, but then there is a big difference from the point of view of the application. Well, when you have many of these rays that can propagate, then at the output you get a speckled output beam. So all these rays and all these modes, they have different phase velocities and group velocities. So just thinking in the spatial domain, they will interfere, and the interference patterns changes completely. So this is just the interference pattern of the near field at the output of the fiber. You just touch the fiber and all these speckles move around. So it looks chaotic. Of course, it's fully deterministic because depends on the relative phase shift between the modes. But so you cannot transport images, you cannot transport spatial information. You have to use some tricks like spatial light modulators and some genetic approach or phase conjugation to correct for this spatial distortion. Whereas single mode fibers, well, they have a single mode. So the beam comes out as clean, a Gaussian beam comes out, which is similar to the one of your laser. So the spatial coherence is by definition, I mean, the beam quality is perfect, is as close as possible to a Gaussian beam that propagates in free space. So that explains the success of single mode fibers for all the applications so far, and they have been used for 99.9% of systems and applications. And again, now going into multimode optical fibers, there are two varieties. So first of all, there are two types of fibers, multi-mode and single mode. That's easy. Then about multi-mode fibers, there are two types. There is a standard step index fiber, which is just a single mode fiber, bigger one. And you see that in this case, for the step index fiber, what I show for the different modes, how the different phase velocity is changing, and you see that they have no regular spacing between the modes. These are the red dots. Whereas if you make the parabolic, the index profile looking to a parabola, a truncated parabola, then is a graded index fiber, which to first order enables you to suppress modal dispersion. So the modal dispersion is much smaller for this graded index fiber, but they have a particular property which is very important, that all modes are grouped by families of degenerate modes, nearly degenerate. So the spacing between each family is constant. So all these modes have equispaced phase velocities, which is something to remember for the following. And then there are other multimode fibers like multi-core, photonic crystal, hollow core, and so on. But we will essentially almost in everything that I will present today, I will talk about graded index multimode fibers. So this is just to show how, for the two different types of refractive index profiles, how the mode look like. So you can study the mode profiles, and something that you can notice immediately, that fundamental mode for the step index fiber is very broad. So the nonlinear, because it's not so confined, the nonlinear coefficient will be relatively low, even lower than the nonlinear coefficient for higher order modes. Whereas for the graded index fiber, the fundamental mode is very well confined, and that is the effective area is small, and the nonlinear coefficient will be high, so will be the dominant one. Okay, and then again, what is the coming to the motivation? Why there is so much interest in the community about multimode fibers? Well, the first motivation comes clearly from the internet capacity crunch, the bottleneck to the capacity of our communication, fiber optic communication lines. So the only way to effectively increase the capacity of optical communication systems is the space division multiplexing. And using multimode fibers is a special type of spatial division multiplexing, which involves molded division multiplexing. So each you can just use one fiber, and if you have a the key is of course to develop all the zoo of components that go around. For example, a multimode optical amplifier that is able to amplify all the modes with equal gains. So, but in any case, this is an effective way to multiply. If you have a multi-mode optical fiber with M mode, you multiply the capacity by M times. Whereas if you just increase the nonlinearity, you increase the capacity by the logarithm of the increase of power, which goes much slower. And then so nonlinear effects will limit you in any case. So that is the really the emerging approach, especially for submarine intercontinental links. Another important application is that if you make the fiber bigger and multimode, then you can substantially increase the energy delivered by femtosecond lasers, both continuous wave and also mod-locked femtosecond lasers. So for many high-power applications that we have today, and we know that the fiber lasers are widely used. They've replaced almost all other lasers in industrial applications, from micro machining to cutting metals and so on. So that is, and having stable and more powerful fiber lasers is a really big challenge. And then there is a motivation from a fundamental point of view, which is the one actually that motivated my grant, is that you can have virtually inexpensive for free, because a graded index, these are standard fibers, so they cost $1 per meter. They are not expensive hollow core fibers that cost thousands of dollars per meter. So you can study light complexity using this basically for free test bed. You can study multimode solitons, spatio-temporal mode locking, super continuum, multimode spectral broadening, so generation of sidebands over ranging from the visible to the mid-infrared, and the spatial beam self-cleaning. So I will say something about these first two effects, these two effects. But first, before going into that, I will give this slide of the perspective of the entire game that we are playing that involves nonlinear effects. What nonlinearity is that you introduce a nonlinear polarization which modifies the material properties with light. And of course, we don't have any quadratic polarization in fibers. We have only the cubic one, the Kerr effect, or Raman, or harmonic generation, supercontinuum and sideband generations. And all these effects are effects which occur, so initially in this plot what you have the input power and the output power. So initially you increase the output power, you increase the input power, and the output power increases linearly. And then in a nonlinear regime you start to have a bending, but still is fully reversible. So if you go down, you don't have any hysteresis behavior. So you increase the power, you go along this line, you decrease the power, you go down along the same line. And so the first part of the talk, I will talk about effects in this reversible domain, and like a self-cleaning. So you see that the beam shape changes the output with power in a dramatic way. You go from speckles to almost a clean beam, and also multimode solitons belong to this range. And then there is a new window that opens here between what is hard breakdown is essentially you have breakdown of the fiber. The transmission drops to zero. You are destroying the fiber, and you create permanent defects by light. So there is a window that has been virtually unexplored so far that we are studying in our lab, where there are many beautiful effects like generation of conical or spiral waves, plasma filaments, and so on. So and we call it extreme soft breakdown type of regime. So I'll just essentially try to show some examples at the end of the talk. So now, starting with the weak nonlinearity regime, what is the framework to study the classical framework, to study nonlinear effects. The classical framework is always based on the nonlinear Schrödinger equation, which is the same equation that holds for single mode fibers. You expand the field on the mode basis, and the modes are the linear modes. That's why it's a weak regime. Nonlinearity doesn't modify the modes, but only affects the slowly varying envelope over a length scale which is relatively long, of the order of the dispersion length and of the order of the nonlinear length that can go from meters to kilometers, depending on the power level. And you get, somehow a straightforward extension of the single mode case. You have now, instead of a single equation, when you have the interplay between dispersion and nonlinearity, so these two terms in the nonlinear evolution equation are, the first term describes chromatic dispersion, and also now modal dispersion, because all modes have different group velocity. And the second term describes nonlinearity. And nonlinearity here is a self-phase modulation and four-way mixing. Okay, so these are complex terms, but again, is just a vector extension of the single mode nonlinear Schrödinger equation case. What is the problem that I anticipate here is that in this nonlinear term, you see you have the four-way mixing, the multiplication between three fields with all these indexes running. So it's okay if you have a few modes, you can compute this, but as long as these fibers that we use in the experiments, they have 100 of modes. So then the number of terms that you have here goes with the cube of the number of modes. So it's a huge number of terms, and it becomes, after 10, 15 modes, it's almost impossible to solve. It needs months to solve this equation. So that is a real practical drawback to use this simple and classical extension of the single mode approach for multimode optics. Is just very complex and very time consuming, even with modern computers. So some introduction to the concept of multimode soliton. So in the linear regime, in linear beam propagation in green fibers, for example, you have three modes, and when you have a short pulse, essentially the strongest effect is modal dispersion. What does it mean? It means that you see you have initially superposition. You send you couple your power in three modes equally. Then they split in time. See, the pulses move away from each other because each mode propagates with a different group velocity. So you have a spreading in time, which is known as modal dispersion. Of course, if the pulse is very long compared to this modal dispersion, then on the other hand, so you can neglect the modal dispersion simply because you have a much longer time scale. And in this case, you have a periodic breathing, a periodic evolution that is called the self-imaging of the beam, that is due exactly to the fact that all the phase velocities are equally spaced. It's like a Fourier series. If you sum a Fourier series, you have a periodic signal, and the same here, you have a beam that you inject, and this periodically is reproduced along the fiber. And so you get an image period. That's why it's called the self-imaging. You image yourself after a period which has a length scale of less than a millimeter, half of a millimeter typically. This is in the linear regime. In the nonlinear regime, what happens is that thanks to the Kerr effect, all these modes lock together. So there is a mode locking effect in time. So nonlinearity, essentially what it does is shift the frequency of all modes so that in order that the frequency of the modes is shifted, so that thanks to group velocity dispersion, the group velocity dispersion induces a velocity shift, which is exactly equal and opposite to the to the velocity shift given by the modal dispersion. So nonlinearity shifts the frequency so that essentially magically all the modes now propagate together, stay together. So that is the essence of this multimode soliton, at least in principle. It works very well. So you can compensate at the same time chromatic dispersion and modal dispersion. And you have a beautiful self-imaging effect also for solitons. That looks very good on paper, but in fact, in the first experiment, when by Reininger and Weiss, where they have studied these multimode solitons, they were a little bit cheating because they actually sent 90% of the input beam into the fundamental mode. So that's very easy. That the other two modes, the other few modes that were excited, I mean, were trapped by the fundamental, just because the fundamental mode had all the energy, so it was naturally trapping them. So when you actually spread the information over many modes, this trapping condition is very unstable and almost non-feasible in practice, unless, sorry for the complexity of this regime, of this slide is very complex, but I'll just try to explain the essence. That there is a special case where multimode fiber solitons are for real. And again, what is the difficulty? The difficulty is that you have to compensate at the same time chromatic dispersion, which is typically occurs over a very long scale, and the modal dispersion, which is much stronger, so which occurs over a short time scale. So how can you compare, you want to compensate both effects with the same effect, which is the Kerr effect, which occurs over the nonlinear length scale. So you cannot compensate the two effects which have a very different length scales. Chromatic dispersion, long length scale, modal dispersion, short length scale. But if there is some pulse, some regime where the two length scales become comparable, then it's obvious that you can compensate them by nonlinearity, because nonlinear length must be equal to to the dispersion length and to the modal dispersion length, chromatic dispersion length and modal dispersion length. So when the two modal and chromatic dispersion lengths are equal, then you can compensate them with the nonlinearity, if of course the power is such that the nonlinear length is equal to the other two lengths. And this occurs only in the femtosecond regime. Why is that? Well, because the walk-off the distance scales linearly with the pulse width, whereas the dispersion length scales with the square of the time width, of the pulse width, right? So if the pulse, in the picosecond regime, this dispersion length is very big, much bigger than the walk-off length. But if you decrease the pulse duration, you see it decreases with the square of the pulse duration. So in the femtosecond regime, this dispersion length goes down, because it goes down with the square of the pulse duration, and it can actually become equal to the walk-off length. So the dispersion, I mean, the modal dispersion length and chromatic dispersion length actually equalize in around 100 femtoseconds. So that is the magic number. And if this is true, then there is, you see, you equate the two dispersion distances, and this means that T0 is unique, is fixed. So there is only one specific temporal duration for a multimode soliton, as opposed to single mode solitons, where, again, you can always have any duration, arbitrary duration of the pulse, because it's enough you change the power. You change the duration of the pulse, you change the dispersion length, but then you change the nonlinear length by increasing the power. But here again, the pulse duration, if you want to have the two dispersion lengths, modal, chromatic dispersion and modal dispersion length equal, then there is only one pulse duration, which is determined only by the linear dispersive properties of the fiber, and of course it changes with wavelength. It doesn't change with power, but only changes with wavelength, and is around 100 femtoseconds in the telecom range. Okay, so that there is a sweet region of pulse durations where these multimode solitons are for real. And in fact, if you send a pulse of very different input pulse width in the fiber, and you always get a soliton of a fixed pulse duration. So you send 240 or 70 femtoseconds in the input, you always get 100 femtoseconds in the output, because the pulse duration is fixed by this relation. So that is just an overview of this effect of the locking of the modes which occurs in this regime. Again, this, in reality, there are other nonlinear effects like Raman scattering, which occur over a longer distance, and this Raman scattering leads to energy transfer between the modes, the different modes, which eventually disrupt this beautiful multimode soliton, and then all the energy is transferred to the fundamental soliton. So at the end of a very long fiber of a kilometer length, you end up with a soliton only in the fundamental mode. So for a while, you create this beautiful multimode superposition soliton, but then eventually it is unstable and it decays into the fundamental mode because of the Raman effect. Now I'll move to the second surprising and the effect which only occurs in multimode fibers. There is no analog by definition in single mode fiber, which is the spatial beam self-cleaning. So the surprising observation is that now there is no time, it's just a spatial effect. At low powers you have speckles, so the intensity profile looks chaotic because of multimode interference. You increase the power and magically all the energy is recombined and you get a clean spot at the center of the fiber, very close to the fundamental mode. But in fact, it's not only the fundamental mode. You see always some energy in the higher order modes. So it's actually a mode distribution that is created. And it occurs above a certain power threshold and is due to the Kerr effect. And so and it's very stable. What is amazing is that you squeeze the fiber, and in the linear regime, all the speckles move around, but you move the fiber around, and this pattern doesn't change at all. So it has some interesting applications, and it has been studied with pulse duration from nanoseconds to femtoseconds, in active fibers, in tapered fibers, in few mode fibers, by many groups, and it has been reproduced. But and also it has application for multimode fiber lasers, because you can make a multimode fiber laser, so with high energy because the fiber is thick, is multimode, but with a clean beam quality at the output, which is essential. For many applications, you need a clean beam with a high m² parameter, and if you exploit this self-cleaning effect in the multimode fiber, which you insert in the loop of your laser, then you win because you preserve the beam quality and you increase by orders of magnitude your pulse energy. So it has applications, we demonstrated applications for high resolution multiphoton imaging in microscopy and endoscopy using this effect. This is self-cleaning. So what I want to do is just to outline one picture which is completely alternative to the classical one based on the coupled nonlinear Schrödinger equations, to explain this effect and to reproduce it, which is in fact has nothing to do with nonlinear optics, but just on statistical mechanics. So the theoretical description of this effect is that beam self-cleaning can be described as a process of thermalization of a nonlinear multimode wave. So essentially the photons in different modes are like particles of a gas in a box, in different regions of a box. So you can compute the number of configurations, the number of ways in which you can set n1 photons in mode 1, n2 photons in mode 2, and 3 photons in mode 3. All these photons are indistinguishable, and you can compute all the combinations. So that is and the GI is the number of the degeneracy of each group of modes. So I is the index of a group of modes which have G modes, which has GI modes with the same propagation constant. So GI is the degenerate. So you can compute this W, and then you maximize the Boltzmann entropy. So you maximize the number of configurations, and if you do this by maximization with the two constraints, which are the conservation laws, which have to be obeyed. That is the number of, because it's a conservative system, there is no dissipation. So the power is conserved, and also the internal energy is conserved, the Hamiltonian. So by imposing these two conservations, you get an equation of state, like in a gas, in a classical gas, which relates them to two parameters, which are the chemical potential and the temperature. Again, these are two effective parameters that describes the optical thermodynamics. It has nothing to do with the temperature that we can measure with a thermometer. We can measure it, the temperature, based on the equilibrium distribution, which is the famous Rayleigh-Jeans distribution. So it essentially tells this formula, which is very simple. It tells in each group of modes, you divide the total number of photons by the degeneracy, and you have these two parameters which depend on mu and t, and they depend also on the propagation constant of that group. This is a Rayleigh-Jeans distribution, which tells you what is the equilibrium distribution. And what is the meaning of this equilibrium distribution? When you maximize the entropy, essentially you determine the most likely configuration of your system, the configuration that is most disordered, okay, which is the most likely one to appear. And where is nonlinearity? And there is no nonlinearity here, it's just counting. Nonlinearity only occurs into the picture because you start from a distribution which is different from the equilibrium one, the input of the fiber, and nonlinearity is like a collisions between atoms in a gas, exchanges energy between the modes. So through four-way mixing, you have energy exchange, which lead to redistribution of the original transient distribution of energy in the modes towards the Rayleigh-Jeans. So the higher the power, the faster is this convergence to thermalization. The faster are the energy exchanges, which lead to the most likely distribution. So it's all in this single slide. And again, this is a picture of how this mode look like. You can take a Laguerre-Gauss mode base, and there is you can number the modes with two indices. One is the quantum number, the one that essentially determines for which quantum number you have a degeneracy GI. So the fundamental mode, the GI is 1, and then 2, 3, and so on. So you have all these modes have the same quantum number, that is the same propagation constant, but different azimuthal index, different orbital angular momentum. And the main quantum number, so these LG modes, they have two indices, and the quantum number is determined by this simple formula from the two indices of the modes. Well, here is just some details how you, I mean, the only slide that is necessary to understand the concept is this one. Then if you want to go into the details, then you can express the conserved quantities, the Hamiltonian, as a function of the number of photons in each mode and the momentum of of those photons. And then you conserve the number of particles, so the sum of the photons in all modes. And the calculations are very simple in the grand canonical ensemble, and you compute the partition function, and from this one you obtain immediately the average number of particles in any given mode by doing the integration of the partition function, which leads to this Rayleigh-Jeans distribution. And then explicitly that's how the temperature and the chemical potential look like in this Rayleigh-Jeans distribution. Is it true, or is it just a dream? So, well, again, just one slide to recall the spatial self-imaging effect associated to the equispacing of the modes. And that's something, again, just to anticipate what I will say in a moment, you can actually visualize it, because when you are in the very high energy regime, when you get this multi-photon absorption, you get upconversion of light from the defects in a green fiber, which is doped by germanium, so there are some defects. And at the points of maximum intensity, when the beam becomes more compressed in space, the intensity goes up and you generate this fluorescence. So you can actually visualize all these blue spots generated by the green fiber associated with this breathing of the spatial breathing of the beam. So how this this Rayleigh-Jeans distribution looks like? So that is that's why the beam is clean, because most of the energy is always in the fundamental mode, and then it goes down with an hyperbole, with this hyperbolic decrease. And if the excitation is symmetric, you have a symmetric distribution along with respect to the azimuthal index. m equals 0. And then we implemented an holographic method to actually measure the distribution. So measure the phase and the power in all the modes at the output of the fiber by using a spatial light modulator. So we could do a mode decomposition of the field at the output actually to verify that this equilibrium distribution is obtained. And this is a result, so it shows the power in the different modes as the power is, the relative power in the different modes as a function of input power. You see that the fundamental mode goes up, and there is a tendency of so growth of the fundamental mode at the expense of the other modes. But then when you do actually a comparison, the power goes up in this way. You see at low powers you have a distribution which is non-equilibrium one corresponding to speckles, and the red curve is the Rayleigh-Jeans distribution. You increase the power and you really approach at maximum power the equilibrium distribution with the error that goes down. So that is a confirmation that indeed this thermodynamic approach is really describing what comes out. And of course, so what I'm showing here is the beam profile that goes from speckles to a clean beam, and the reconstruction using the result of the mode decomposition. So just to confirm, if they look the same, this means the reconstruction is correct. So it's just as a confirmation, the second plot. And and of course we confirmed not only that the distribution is the one that we expect, so this also shows that the self-clean beam is in reality not just the fundamental mode, but it has substantial energy, almost 40% in the higher order modes. Just the dominant one is the fundamental. And also we confirmed that internal energy or Hamiltonian and the orbital angular momentum are conserved. So that is a sanity check that the method works. What happens if you introduce some beam which has an orbital angular momentum? I will go very quickly. I don't think I have much time for that. Well, it just leads to a symmetry breaking of the distribution. If you introduce an OAM, then the distribution is no longer symmetric with respect to m equals 0. And so also we did experiment to confirm that. So just believe me, I will not go into the details, but this asymmetric distribution that is predicted by the theory in the presence of OAM, it was also confirmed experimentally. And also I would like to notice that here is a thermalized beam, but it doesn't look clean. So in this case, it shows that you can have a thermalized beam that is an equilibrium beam distribution, which does not necessarily have a symmetric bell shape. So the quality factor of this beam may not be high, but still is thermalized. That is absolutely stable if you move the fiber, whereas here you are out of equilibrium and the speckles move around. So the thermalization is, I would say, a more general concept than self-cleaning. So self-cleaning, you get it only in a specific range of input coupling conditions and powers. And how to seed this OAM beam? Okay, you can generate an orbital angular momentum beam by many ways, by some lenses or spatial light modulator, but there is a very simple way. Just inject a laser with some tilt angle and an offset with respect to the axis, and then the beam will evolve along an helical propagation in the fiber. And you can compute the theoretical value of the average angular momentum of this beam is just a function of this tilt and the offset. So y0 and theta determine the orbital angular momentum. And it is interesting that under some conditions that I will quickly describe in the following, what comes out from the fiber at high power can generate a supercontinuum that distributes itself along a spiral. And in fact, this effect results from a combination of two effects: a spiral emission, that is emission of a beam with the spiral-shaped intensity profile, which occurs also at low powers. So even we reproduced this figure with the helium laser, or even with the laser pointer like this. So you obtain a spiral beam with appropriate coupling conditions. And at high powers, there is a supercontinuum generation and so-called conical emission, which occurs in free space, but also in multimode fibers, so separation of colors. When you combine the two effects, you get what we call a rainbow-like spiral profile. And this it can be achieved under different configurations. So we understand this spiral emission as a manifestation of a beam that carries an unconventional longitudinal orbital angular momentum, that is an angular momentum that varies not linearly with the azimuthal angle, but not linearly with the power of the azimuthal angle. So that is the phase of the beam varies with a certain integer power of phi, where phi is the azimuthal angle. And we have there are two ways to generate these helical beams in the fiber, either by coupling the beam into the cladding. So that is what we have here is a simulation, and that is the experiment that confirms it. Or you can and you obtain a helical plasma filament plus spiral emission, or you can get it also coupling in a graded index fiber the beam in the core. So you can couple in the cladding. So the beam, of course, in the cladding it expands, but it moves along to a helicoidal trajectory. And it can also move with a helicoidal trajectory if you couple it into the cladding, and you get also a helical plasma filament at sufficient high powers. So again, to connect this with the plasma theory, what we have observed with these helicoidal beams. So plasma is typically observed in propagation in free space of laser beams. It acts as just associated with the ionization of air, and it acts as a divergent lens. So it tends to broaden the beam, and but the Kerr effects tend to self-focus the beam. So the two effects can balance each other. So it's like a spatial soliton that is formed. And you can have the equivalent of the spatial soliton is what is known as a plasma filament. And of course, it can also be associated to supercontinuum generation. And the nice thing is that generally these plasma filaments go straight. And in a fiber, it's interesting because you can, by using this cylindrical geometry of the fiber, you can produce plasma filaments that are curved, that move around. So there are many applications of plasma for material modifications. For you can generate, because you can modify by ionization the material. So you can write a Bragg grating or a waveguide that moves helicoidally in the fiber. You can use them as an optical tweezer to trap particles for micro machining and so on. So there are many applications. And again, also by solving the 3D plus 1 or linear Schrödinger equation in space, it's just a spatial effect. We confirmed how these plasma filaments are, we reproduced the generation of these plasma filaments both in graded index and in step index fibers. And there are some differences. For example, the pitch of this helix doesn't change when you change the injection conditions in graded index fiber, whereas in step index fiber, the period changes when you change the coupling conditions. So there are some detailed differences. And again, the nice thing is that we can visualize these plasma filaments, again, because of this luminescence that is associated to the presence of defects. For example, even in pure silicon fiber, there are some defects called known as non-bridging oxygen hole centers, which emit in the red 650 nanometers, and so you start from near infrared 1030 laser. You absorb several photons. You go to this excited state, which then decays, and you have the emission of this luminescence, which enables you to visualize the plasma filament as a red beam. And similarly, in germanium, you have in graded index fiber, you have germanium doping, which and in germanium there are other type of defects, which now radiate at 400 nanometers, so it looks more bluish, the light. And so you start from a self-imaging, you see only a certain number of fluorescence at bright spots, and then you increase the power, and all the spots are connected into and you get a self-channeling plasma filament by connecting all the spots along this helicoidal trajectory. And okay, these are just some details of the characterization of this multiphoton absorption process. I will move, I think it's time to move to conclusions. And so in the regime of weak nonlinearity, I think one key result is that we have validated the description of this surprising beam self-cleaning effect as a manifestation of classical wave thermalization, and demonstrated by holographic mode decomposition techniques, leading to this Rayleigh-Jeans equilibrium mode power distribution, verified the conservation laws, and generalized to beams with orbital angular momentum. And in a strong nonlinearity regime, we have unveiled many cases by chance, just seeing what happened and then understanding, of course, the physics behind several novel effects which occur in this extreme soft breakdown regime, like the presence of a strong multiphoton absorption and upconversion luminescence, spiral beam generation, rainbow supercontinuum. Actually, this image was Wayne Knox from Rochester University liked it so much, so Optica took it as the icon of a Nonlinear Optics conference in Hawaii of next year. So if anybody wants to go to Hawaii, this is not from some Hawaiian painting, it's actually from our lab. And so helical plasma filament generation, and we are now working on applications of these effects for tweezers and also multiphoton microscopy and endoscopy. Try to use this for something useful. Thank you for your attention. I'm sorry if I was going too fast. Nobody interrupted me for questions. But now, please.
Okay, now it's time for questions or comments. Okay, one question over there.
Wait. Thanks for the talk. Correct me if I didn't understand correctly. This orbital angular momentum, like if you can separate it in time, I was just wondering if you know any application like in sensing particles or something where you might have like improvement of temporal resolution or something like that could happen?
Well, you can, as I said, one idea is to use for tweezers, so using the orbital angular momentum for trapping particles and imparting to them an orbital angular momentum by using light.
More questions?
Yes, it could have applications in sensing as well, yes.
Yeah, more questions? Yes.
Thank you very much for your nice talk. And I was listening when you were talking about the difference between the solitons in a standard single mode fiber and the solitons in a multimode fiber. You were pointing that you need a specific time duration.
Right.
I'm wondering if you need also a specific power. And in that case, how is that the soliton is stable? If you need to fix both time and power, it looks like it should be quite unstable.
No, it is stable in the sense that it is like an attractor. It behaves like in a dissipative systems. In dissipative system, you have an attractor. So the soliton that comes from a fiber laser is called dissipative soliton, and it has a fixed duration and power. Of course, when you couple into the fiber, you send much more power, and the excess power will be dissipated into dispersive waves, or maybe you generate many of these solitons. But just saying that what comes out from the fiber, it has a specific time duration and power. But if you have twice the power, maybe you generate 2 solitons, each with that. So a pair of solitons, a multiplet.
There was another question here. Yeah.
I have 2 questions only to repass a concept. Can you repeat which importance have the potential chemical chemistry and the modes of Laguerre-Gauss, please?
Laguerre-Gauss are the modes of the multimode fiber.
The importance of the modes Laguerre-Gauss, please. Can you repeat which importance is in modes, please?
Well, these are in the linear conditions. These are the modes supported by the fiber. So they are an orthonormal basis, and you can express the guided field as a linear superposition of those modes. So there are different families. There is so Laguerre-Gauss is the most used for. There are also Hermite-Gauss modes. You can use another basis.
And the other question is about the potential chemical. Can you repeat which importance have in the fibers?
Well, the chemical potential. Again, the temperature, chemical potential are optical parameters which are determined, are associated to the equilibrium distribution. So you can only determine them a posteriori based on the distribution that you observe. So they don't have, they have just, in fact, they have a physical meaning, but again associated with a statistical description of the mode population. They have nothing to do with chemical potential and temperature of a gas or associated with the collisions between particles.
Okay, thank you.
Yeah. Any other question?
So, thank you for the talk, Professor Wabnitz. I have a couple of questions regarding the beam self-cleaning. So you mentioned that the nonlinearity, the forward mixing, has not an essential, a crucial role for getting this kind of evolution.
No, it has maybe the equilibrium distribution is determined just by probabilistic considerations.
Yeah.
So the nonlinearity does not determine the final result.
So does it mean that a system, sorry.
Yes, it just determines the length scale over which thermalization occurs, because it favors exchange between between the modes. So because you start from a different distribution, so you need to shake somehow to make the modes talk to each other, to transfer energy, to arrive to another distribution.
Does it mean that for an optical system with a high enough number of modes, with other types of nonlinearities, this type of evolution would still be observed?
Sure, yes.
Okay.
In fact, yes, you can observe with any nonlinearity. Even if you had a quadratic nonlinearity, you would observe it.
And my second question is actually about you mentioned that, the evolution of the system is thermodynamic, so qualitatively speaking, the disorder is increasing. However, when looking at beam self-cleaning, one would say that, well, the order is somehow increasing, right? So could you please, I'm not sure if I'm wrong, but it's like if the energy is accumulating in only one mode.
No, well, precisely, it's a distribution. So most of the entropy is actually in the higher order modes, in the tail of the distribution.
Okay.
So even in the limit where you have 99% in the fundamental mode, but still you have this 1% in 99 higher order modes which have a high entropy.
So, and it's that contribution which increases the entropy.
Right.
Okay, thank you.
I have a question myself regarding these orbital momentum experiments. Does the circular polarization play a role there? Because you would have like a total momentum, right? You have the orbital one plus the spin from the photon. Does it play a role or not?
Well, it's a different type of angular momentum. So we are also studying polarization effects in self-cleaning. We are studying them, and we find some like eigenstates. For some polarization states, self-cleaning occurs earlier. For others, it occurs later. So there is clearly polarization dependence, but so it's quite still not understand what's going on. I mean, it's quite complex. We have a paper on that.
Okay. Other questions? Yes.
So one could say that the most important feature of the system is, for this particular behavior and description, is this property of its equidistance between with energy mode. So which is basically the optical analog of a harmonic oscillator, a two-dimensional harmonic oscillator. So I guess that there are some properties, including statistics properties, that somehow will be common to both. I don't know if, for example,
in fact, again, the waveguide structure enters into determining the modes, but the equidistance of the modes, where it really is important, is because when the modes are all equidistant, it's easier to phase match four-way mix in terms. There are many, and also the energy exchange is more efficient. That's why you see this self-cleaning in graded index fibers, but if you have a step index fiber, you could observe it, but over much longer length or much higher power, where maybe you destroy the power. That's why nobody has observed it in step index fibers so far.
Okay. The second question is related to orbital angular momentum, because in your system, orbital angular momentum is conserved because of the symmetry of the, because you use a fiber which has rotational symmetry, and the type of nonlinearity curve preserves this condition in propagation.
Yes.
So my question is, have you studied what happens when you use discrete rotational symmetry, and then the spectrum, the angular spectrum will change? It won't be exactly the same.
Sorry, what kind of symmetry?
You take a graded fiber, but not with full rotational symmetry, like hexagonal one.
No, that's interesting. No, we didn't study that.
Because then the distribution, it will change. So I don't know, the statistical properties will remain.
You cannot impose the conservation anymore. Then one conservation less. Yeah.
So it's
the distribution will be different.
It's an open question then?
Yes, no, and we never studied that. It's an very interesting point.
Okay, thank you very much.
And in fact, there are also these square fibers which are chaotic, and it will be very interesting to study self-cleaning effects.
I see. That's good. Any other question or comment? If not, please, let's give a hand again to our speaker today.
And for people of Mairo, now we will go to have lunch, to Farmacia. Please, follow. Follow us to the cafeteria.
Collaborators, in particular in Limoges and in Dijon, in France.
You were there for a long time, right?
Yeah, for 10 years. 10 years. Well, as you said, I was a couple of years with Alcatel, and then 2 years in the United States.